And we are recording. So let me hand over the floor to group two to share with us their presentation. Design is called Hive, which I particularly like. So over to you guys.
So you guys can see my presentation screen?
Yes, we can.
Okay. We are group two, representing Heliostats Improving Vegas Energy, or the Hive. Our team consists of 7 University of Florida students: Aiden, Tyson, Logan, Pedro, Alexi, Caitlin, and James. As a brief overview of our presentation, we will introduce the group's Hedgehog Concept, then provide the product overview and functionality, the key features of the module design, engineering analyses of critical components, a total cost breakdown and analysis, and finally provide a synopsis of this proposal. Our group's unifying Hedgehog concept that identifies the group's core value proposition is to have the overall best efficiency of the heliostat module. This includes consideration for having the most efficient heat transfer qualities, durability of the unit over time, and resistance to ambient desert weather conditions in Las Vegas, Nevada. Heliostats are devices used to reflect sunlight in a desired direction toward a receiving target to provide energy. The aim for this project was to conceptualize and design a heliostat module and array capable of satisfying a collection of customer needs. To accomplish this assignment, the Hedgehog concept is employed such that the project will be built around the idea that our module will have the best overall efficiency while performing all customer needs. The Hive concept was divided into 4 subsystems.
The support structure is made up of 4 L brackets that create a rigid structure that can resist high wind loads. The support structure was designed in this manner to allow for the motors and belts to be easily installed in the structure and to be removed for any potential maintenance after operation begins. The L brackets are spread apart in order to increase the stiffness of the support structure, and the 2 ground anchors are used in order to hold the heliostat to the ground so that the heliostat does not rotate.
The reflective surface acts to redirect sunlight into a receiving aperture in the central tower, concentrating it for energy applications. This design is composed of a highly reflective polymer film attached to a sheet metal frame, which is a cost-effective alternative to traditional glass mirrors. The film is also capable of withstanding extreme weather and heat conditions, making it suitable for this environment. The film is attached to the sheet metal frame with its pressure-activated adhesive backing and flattened to avoid air bubbles and defects to ensure the flatness of the reflective surface.
The field layout is the arrangement of modules in the field to provide optimal combined reflection into the tower. Our design utilizes a commercial PS10 field layout, which was developed using HFLD code using boundary constraints to produce an optimized orientation for heliostats around a central tower. The arrangement follows a radially staggered design in which the heliostats become less closely packed the greater distance they are from the tower in order to reduce shading and blocking.
Finally, the controls subsystem relays information between the module and the computer. This module uses a sun path algorithm, which features a coding algorithm that predicts the length of the sun each day according to the time of the year by referencing weather patterns and astronomical data. This simulation offers very high degrees of tracking accuracy and is not affected by outside distracting stimuli that can alter the results produced by optical tracking methods such as sensors. To control the motors and to communicate with the central tower, a Raspberry Pi Zero was selected. This microcontroller can use Wi-Fi and Bluetooth in order for signals to be sent between modules. This allows the sun tracking to be done by the central receiver, and the signals are sent to individual modules wirelessly.
This animation will demonstrate how our heliostat operates throughout the day. It should be noted that this only shows the moving parts of the system to demonstrate the subsystem interactions. Parts of the support subsystem, including the base plate, ground anchors, and control box, are not pictured, but they act to support the heliostat and relay information. So this is our heliostat. It receives control information based on the sun positioning predictions from our control subsystem, a solar tracking algorithm. This information is converted into a needed rotational output from the NEMA motors that propagates displacement to the frame through a pulley belt. These pulley belts are attached to brackets loaded to the frame, which cause axial rotation of the reflective surface subsystem. The U-joint shown allows for biaxial rotation to adjust the position of the reflecting surface throughout the day. The usage of 2 motors and pulley belts are therefore required for this biaxial motion. Each helio in the stat will be independently controlled, and by arranging them in the PS10 layout, we have worked in maximizing efficiency of our design.
Here are some key features included in our Hive module. This includes the pulley system, universal joint, Reflectech film, ground anchor, and control box. The first is a pulley system, which is used in place of a traditional azimuthal drive motor to direct the reflective surface along the dual axis. Rubber timing belts are highly durable and are used to actuate the reflective surface and prevent slippage. Heavy-duty zip ties are used to secure the timing belts. This movement is then propagated through the universal joint, or U-joint, which is a cross-shaped device that allows for biaxial rotation.
As mentioned before, the traditional glass mirror surface is replaced with a cost-effective polymer reflective film. The Reflectech mirror film was chosen, which is a lightweight, waterproof, weather and heat-resistant material. Reflectech mirror film is currently in use in the National Renewable Energy Lab for use in heliostat applications such as this. The film is a thin, specular reflector with 94% reflectivity. And as research shows, when used at a working temperature of 160 degrees Fahrenheit, there was no degradation of the material and exposure to UV radiation, no discoloration, and no reduction in the reflectivity of the material.
The ground anchor is made of a heavy-duty metal. Each module uses 2 ground anchors to prevent rotation. It's simple to install by drilling the post into the ground using a power drill. The module frame is then placed over top. The round hook has a threaded bolt that is then screwed into the post, securing the module's frame to the ground anchor. This sandwiches the metal frame in between the 2 pieces that make up the ground anchor. It has a black powder coating to prevent corrosion and is capable of anchoring objects during high wind speeds. We found this to be the most simple and cost-effective solution to keep the module grounded.
Now, the control box main components consist of an AC-DC converter, a Raspberry Pi Zero, motor drivers, and a casing that is 3D printed using ABS plastic. There are 2 motor drivers that each control their own respective NEMA 23 stepper motor, rotating pulley system that positions the reflector for optimized solar concentration. The control box is secured to the base plate through 2 mounting fasteners and is high enough off the ground to avoid flooding.
The first subassembly is a support structure. Its purpose is to hold the reflecting surface in place while maintaining it stationary and anchored to the ground. The support structure is partially or completely responsible for satisfying some customer needs. Our product has a module area of 1 meter square, mostly occupied by 1 heliostat. The support structure is designed to have 20 years of lifetime. Also, this subassembly has a low corrosion risk. The reason it can withstand the weather and ambient conditions of the desert in Las Vegas.
The support structure is made up of 16 gauge steel L brackets to hold the heliostat. The motors are mounted in steel boxes to protect the motors from the environment, but the motors are rated to a B insulation grade. The U-joint is bolted to the top of the support structure, and all other components are welded together. And then the L brackets are used to easily mount the motors and allow the belts to travel through the support structure. The belts must be directly below the axis of rotation so that the belt maintains the correct tension throughout operation.
In order to fulfill the objective of lasting over 20 years under the given weather conditions, the ultimate strength of the ground anchor is considered. The ultimate uplift capacity, Q, is calculated using the ground anchor dimensions, undrained shear strength of cohesive soil, similar to the conditions in Las Vegas deserts, and an uplift capacity factor, NCU, found using the embedment ratio into the ground and the charts to the right.
For the control box, a heat transfer analysis was performed to ensure that the temperature inside does not exceed the thermal design power of 85 degrees Celsius as defined for the Raspberry Pi. A closed system thermodynamic analysis was performed. Using an energy balance, the heat in and the work out terms go to 0. And if we perform a steady state analysis, the differential energy term goes to 0 as well. Therefore, from this, we can see that the work in is equal to the heat out. With the work in, that is equal to the voltage times the current taken in by the Raspberry Pi Zero, which is 11 watts. The heat out is as defined before, is equal to the work in, and that is the radiative heat transfer coming off of the control box surface. From the previous slide, it was shown that these are both equal. Therefore, the radiative heat flux out is 11 watts. Using the equation for the net radiative heat flux for an opaque surface, the emissivity, the absorptivity of ABS plastic, the Stefan-Boltzmann constant, the control box surface area, and the incoming solar flux of 1,367 watts, we can rearrange the equation to solve for the surface temperature. And we can find that to be 77.7 degrees Celsius. Now, this is lower than the thermal design power of 85 degrees Celsius, and even with a slight temperature gradient within the box, this ensures that the electronics will be cooler. Additionally, convection with wind, which will occur in the desert, will cause further cooling of the system, but was not accounted for in this bounding case.
Our second subassembly is a reflective surface, which is composed by a metal sheet plate with a reflecting film adhered to it that is responsible for reflecting sunlight efficiently to the receiver. In order to do so, it causes 0% shading area on the module with a reflecting area of 71.5%, which is greater than 2/3 of the module area. The film used is durable, waterproof, and has no performance loss under high temperatures from 30 to 60 degrees, for example. It is washable, and the traditional cleaning methods can be used to ensure 20 years lifetime.
So we know that the first thing that really stands out about our design is the giant hexagon reflector. And you're probably wondering why that instead of a traditional rectangular one. So, and that all boils down to this concept known as the safety area. A heliostat device not only needs the area equivalent to the space the reflector takes up, but also an empty zone around it to act as a buffer between different modules and prevent collisions during operation. This is known as the safety zone and is best quantified as a perimeter circle that is formed by the outermost points of the reflective surface. It's designated by that red circle on the images to the right. For the same reflective area, as the number of edges the surface has increases, the perimeter of the needed safety area decreases. To demonstrate this, look at the images again, and you can see several different geometries there that comprise the same reflective area. The square and rectangular shapes require the largest safety area, while the hexagon needs much less to function. Also, it can be seen that as the edge count increases, the ratio of reflective area to safety area also increases, which allows for more utilization of the zone instead of it just being empty buffer space. So hexagonal reflectors can be spaced closer together to fit more modules in a field, and due to the basic better safety area utilization, they generate high shadowing and blocking efficiencies. As evidence of this, a study was conducted between a field optimization with square cut reflectors and one with a pentagonal shape, and found that the pentagonal field produces a 0.9% improvement of blocking efficiency and a 0.6 improvement on overall energy production. It went on to suggest that reflectors with more edges would actually perform even better, which makes the hexagonal shape a high efficiency reflector geometry that will increase field performance.
Since our reflective frames are made out of sheet metal, it's very thin, so an analysis was performed to determine whether this frame will not yield against wind loads during operation. The Department of Energy design wind speed before the stowing position of a heliostat is about 22 meters per second or 50 miles per hour. So before this wind load is reached, let's assume that the frame is fully vertical at this wind speed. And it should be noted that this full verticality will never actually happen during operation, but this is an extreme case for the heliostat position. If we convert the distributed wind load to a point drag load on the centroid, acting at the centroid of the upper half of the reflecting surface, this results in a bending stress of 136 MPa, considering the frame as a cantilever beam. With the frame having a yield strength of 285 megapascals, the frame is therefore protected against these wind speeds and will not yield.
When wind speeds are greater than 22 meters per second, the heliostat will be oriented in a stowed position. This is demonstrated in the image to the right, and it will protect the device during rough weather conditions. The objective now is to determine if the support can withstand these winds and brace the heliostat while it's stowed. Las Vegas can experience wind speeds up to 82 miles per hour, which is Category 1 hurricane conditions. So, to be safe, we conducted a static force study on our support using the equivalent of a 90 mile per hour wind load. The results are shown to the right. Produce a drag load of 707 newtons and a maximum stress of 260 megapascals at stress concentration points, with the support yield stress being 285 megapascals, is protected against this load. It should also be noted that the support deflection was also very low during this test. As seen in the top right figure, the maximum deflection was less than 2 millimeters at the top of the shaft.
Additionally, for the reflective surface, we performed a heat transfer analysis to determine the emissive radiation coming off of it. If we assume the backside of the heliostat to be well insulated and it's an opaque medium, the radiosity J can be calculated using the following equation. Radiosity being defined as the rate at which leaves a surface per unit area. For the assumption, using reflectivity of 0.94 and an emissivity of 0.03 for very shiny surfaces, the radiative flux, and assuming that the radiative flux from the sun to the atmosphere of the Earth is 1,367 watts per meter squared, the radiosity was calculated as 1,363 watts per meter squared. This flux assumption was made due to the rare appearance of clouds and other reflective atmospheric elements in the Las Vegas environment. If we multiply this flux by the surface area of the reflecting surface, which is 0.175 meters squared, the power out per heliostat was found as 975 watts.
The next subassembly is a field layout. It is a PS10 orientation, which consists of a radial stagger pattern from 3 to 100 meters from the receiver tower on a flat topography. This layout has a heat input of 1.61 megawatts and a concentration ratio of 1,178, overcoming the minimum need of 1 megawatt and 1,000 concentration ratio. It has 3 meter spacing between rows to allow cleaning vehicles to fit.
Now, this analysis is for the PS10 orientated field lab. The objective of this analysis was to determine the angular range of the heliostats. For this, we assume that the central tower is 100 meters high. The minimum distance between the tower and the first module is 10 meters, and the maximum distance is 100 meters as stated in need 14. As a result, the angular range was calculated using simple trigonometry as shown in the following images. And the minimum angle is 45 degrees, and the maximum angle is 84.3 degrees.
By calculating the cosine efficiency, we were able to determine the locations in the field layout where the efficiency is higher and lower. The equation shown was the one used for this analysis, where E, C, and N are the orthogonal coordinates, and alpha and capital A are the sun's altitude and azimuth angle, respectively. They were used in a range from 0 to 90 degrees. It was found that the greatest efficiency happens at the sun's highest point, which is 90 degrees of altitude and 90 degrees for the azimuth angle. And the more efficient locations are those center and closer to the receiver.
The objective of this analysis is to determine the number of modules that the field can support. To do so, we made an approximate field model with a maximum module distance of 100 meters from the receiving tower, as stated by need 14. This model field was found to have an overall area of 10,302 square meters, as depicted in the shown figure. Modules were determined to be oriented in rows across the field, with there being 3 meter spacing between rows to satisfy need 17. If you look at the figure, this is exemplified by the black dashed lines that follow the curvature of the field, but it is not shown to scale. With this layout, each module will require 4 square meters of spacing, and so 2,575 modules can be supported by the field. The commercial PS10 layout was found to have an overall optical efficiency of about 64% from modeling accomplished through code HFLD. Due to the small scale of our field, realistically, the optical efficiency will be much higher. Looking at the modeling results, it can be seen that in the 100 meter range from the tower, which is that red area in the figure, the efficiency hovered around 84%. This makes sense because as a heliostat gets closer to the receiver, light spillage decreases, allowing for a higher efficiency. However, since no experiment was conducted specifically for a 100 meter range, the overall 64% efficiency will be used and can be treated as a lower bound of performance. Applying this efficiency to the total reflective area, which is found to be 1,841 square meters, Assuming a reflective area of 1 meter squared, the concentration ratio is about 1,178 suns, which is above the needed ratio of 1,000 from need 13. The number of the modules in the field also allows for the total thermal input to be determined. Using 64% optical efficiency, and knowing that each module produces 975 watts of thermal input from the film analysis, the total thermal input can be found from multiplying the efficiency together with the heat input of each module and the total number of modules, which is 2,575. This results in a total thermal input of 1.61 megawatts, which is well above the needed 1 megawatt stated by need 12. This energy production is from rows of heliostats that are spaced 3 meters apart. The layout can be improved to even higher performance though by utilizing a close packed configuration of modules by taking advantage of the low safety area a hexagonal reflector gives. The possible arrangement is shown to the right, which depicts heliostats from 3 rows in a staggered alignment that allow for modules to be oriented closely together and increase the number of units in a field. If we did not have the required 3 meter spacing from need 17, this would be the optimum layout configuration. But in order to satisfy this need, module rows are currently considered to be 3 meters apart. However, we propose to allow several rows of modules be close packed, and then have spacing for a vehicle travel. This will increase field performance while still allowing for adequate washing procedures to be conducted, and thus would be the highest performing field configuration. Really quickly though, let's repeat the process of finding the field thermal input, except now on a much larger scale to compare against the current commercial PS10 performance. The actual PS10 location uses 624 heliostats that are much larger than ours, about 120 square meters of a reflected area each. And it's designed for a location about 37.4 degrees north. Our design is designated at a 36 degree north location, so they're similar enough for us to be able to compare them effectively. Making this comparison, our small scale field actually greatly outperforms the current commercial location. Modeling a field with a maximum module distance of only 500 meters, our layout can support 58,178 heliostats, produces a thermal input of 36.30 megawatts. So our design can match the PS10 field performance with a massively smaller field area. This will reduce costs for field purchases and cleaning operations, and will also lead to a better optical efficiency due to the closer positioning of modules relative to the receiver. Therefore, our heliostat is overall a better performer than the current PS10 location and is preferable for development.
Our last subassembly is a control system. It is responsible for tracking sunlight throughout the day efficiently with little to none error. The control system works through a 1 Raspberry Pi 0 per module, controlling the 2 motors. It has a tracking error of 0.035 degrees and can target the receiver in a range from 10 to 100 meters. Also, those motors are insulation class B in order to withstand the desert climate conditions.
Using the variations of planetary orbit theory and resources like the astronomical algorithms, the position of the sun can be predicted with high accuracy throughout the day. Using this simulated sun path, the heliostats can be oriented for maximum reflectivity. Our customer, Dr. Sheffy, provided a code at the beginning of the project that found the optimal normal vector of the heliostat with a given sun and tower altitude and azimuthal angles. The provided algorithm itself is very much a base, but the next steps are clear. With a given heliostat position in the field, the tower angles will be known, and the sun angles will come from the code prediction. This method can be applied to the whole field to achieve optimal heliostat orientation. The National Renewable Energy Lab uses similar code to this, which they call the solar position algorithm. The SPA has shown to provide tracking accuracy within 0.0003 degrees and outperforms optical tracking methods by 2.1%. It can also remain operable during suboptimal weather, like cloudy days. The Raspberry Pi Zero that we're using in the module is Bluetooth and Wi-Fi capable, which will allow communication between the heliostats without running cables across the entire field. The only cables that would be required would be the AC power source to each heliostat module. This removes the need to maintain signal cables across the entire field, reducing maintenance costs. The motors that we're using in the module are NEMA 23 motors with a maximum torque of 1.26 newtons. The motor torque was selected based on wind speed calculations. Motors can be rated with a 60-mile-per-hour wind differential across the entire heliostat module when it's in the vertical position, but it should never be in a vertical position in this wind conditions because it will move into the safety configuration past 50 miles per hour. The angles shown in the diagrams on the right show the maximum and minimum angles for each heliostat axis. The minimum angle is 2.856 degrees for a tower that is only 10 meters tall, and the maximum angle that a heliostat would need to reach is 134.5 degrees for a tower angle or a tower height that is 100 meters tall. The motors have 200 steps per rotation to allow a high resolution of motion to track the sun throughout the day. The belt system that is in our heliostat module acts as a gear reduction in order to move the mirror at a maximum displacement of 0.07 degrees for each step of the motor. The error that is due to the discrete steps of the motor is half of the change in angle for each step, which leads the error to be 0.0535 degrees. To move the full 90 degrees that will be required on any given day, the motor will have to move 1,286 times, incrementing one step every 33.5 seconds. The maximum rotation speed for the motor is 400 RPM, which is well above what will need to be required by the heliostat module.
Now, even perfect designs need regular maintenance. To ensure consistent performance over the field, the heliostats will be cleaned regularly. The field will be split into 5 different zones, with each zone consisting of 515 heliostats. The zones will be alternated daily. The daily cleaning procedure will consist of operating a vehicle between the module rows and spraying down the heliostats with tap water at about 500 psi, which was found to be able to cover up to 95% of reflectance from heavy dirt buildup. Throughout the year, at the end of every quarter, a field survey will be conducted to check for needed maintenance for any of the major components.
The overall cost includes raw material, off-the-shelf parts, manufacturing of the raw material, assembly time, including labor and energy consumption of the equipment used. We created 2 cost breakdowns for a better understanding and comparison between building a prototype and mass producing a field of heliostats. The mass production price is the price per heliostat when building a field of 2,575 modules. Since the design is slim and simple, the manufacturing and assembly costs are low. Most assembling is spot welding since the majority of the structure is made of 16-gauge steel sheet metal. In order to be conservative with our numbers, we assumed the manufacturing, assembly, and energy consumption costs remain the same. Although the cost is above the customer need of $100 per meter squared, we wanted to make sure that we had the most efficient system, which increased the cost. For high volume orders, manufacturing and assembly time will decrease, bringing the price per heliostat down. According to the U.S. Department of Energy, the average heliostat on the market is approximately $127, so we worked hard to keep the cost below the average. Our unique design is created using different manufacturing techniques in order to build a highly efficient system. The unique pulley system allows for minimum error in the system, and the overall module is built for a long-lasting lifespan in harsh environments. Current solar farms have issues with maintenance, especially with glass reflective surfaces, since they tend to shatter from outside events. This causes the heliostat to be useless and would be expensive to replace. We chose not to use glass in order to keep costs low and allow for easier maintenance. The slim and compact design allows for close packing in the PS10 layout while also reducing shading with the hexagonal shape of the reflective surface. The hexagonal shape is also visually appealing and breaks the norm of squares and rectangles in the field. This may not be a concern to the cities who will be building these fields, but residents might not want to see visually unappealing energy plants near their homes. A more aesthetically appealing heliostat field would attract those interested in solar energy and innovative technologies. This would then encourage customers, such as businesses and universities, to purchase our product as an amenity to attract more patrons to their facility. This then expands the original customer audience and therefore increases total exposure and revenue for the product. A potential example would be the UF Honeybee Research and Extension Lab, as shown in the picture, whose artistic exterior attracts visitors. Our goal for this design was to strive and meet all customer needs while also exceeding the customer's expectations. We wanted a simple, slim, efficient design with high thermal input and low tracking error in order to provide optimum efficiency. Thank you for joining us today and listening to our presentation. If anyone has any further questions, feel free to ask.
All right, great. So that was 29 minutes, almost to the second. So we've got just over 15 minutes of Q&A. And before anybody else jumps in, I just wanted to say, and you guys know this, we talked about this in the design reviews. I really appreciate the focus on trade dress, right? Like using that hexagonal shape and demonstrating that it is good from both a material saving point of view, an increasing area point of view, an aesthetic point of view. And you guys added a bunch of stuff here that I haven't seen before. I really like the example of the beehive facility. So I think that was really cool, right? It's we talked about in the IP section of the class, design patents and trademark. And I think you guys of all the groups, I think did the best job sort of conveying a cohesive trade dress idea. So I really appreciate that. But let me hand it over to the rest of the panel and see what technical questions people have.
I was waiting for somebody else to go first, but I can jump in.
Go ahead.
Okay. So I'll hit on the FEM again. You guys did a FEM of a cantilevered beam, albeit with a somewhat complicated section, but it's a cantilevered beam, right? So that's not something that rises to the level of complexity that I would expect to need a FEM. A hand calc, MC over I kind of calculation is more than sufficient for what you need there. But given that you did do one, can we flip back to that side, and I'll ask a couple of questions on that. There it was. Yeah. So you're saying that you did an analysis, I guess, with a 90-mile-an-hour wind. Is that based on some probabilistic assessment of what a maximum wind speed would be, and what is that?
Well, the maximum wind speed Las Vegas can experience is 82 miles per hour. The reason we chose 90 miles per hour is actually because of interaction with you at the post presentation. When looking at it, you asked us if it could withstand 90 miles per hour, which is why we chose that. Okay. I wouldn't rely on me. I know very little about wind. But I will say that wind is a probabilistic thing, right? So, just like you hear about like a 1,000-year flood, you'll have like a 1,000-year wind event, right? And so your customer probably has some idea in their head that if this thing should last 20 years, maybe we want a 100-year wind event or something like that. And if Las Vegas in its recorded history has experienced wind speeds of up to 82 miles an hour, maybe that's sufficient. But there's probably some probabilistic distribution of wind that you can expect, and so I'd look into that. Then you noted that the highest stress that you saw in your FEM was 260 megapascals, right? I'm assuming that happens at some stress concentration that probably isn't very well represented in a FEM. Yeah, it was going to be at that top welding plate that connects the 4 L brackets together. Oh, it's at the top? I think it was, but then I think, Aiden, do you remember where it was exactly, actually?
So the brace that's going across about 3/4 of the way up, that mounting point where those two plates are welded together was the location of the stress concentration. Yeah, I would guess that's a sharp corner in your FEM, and FEMs are notoriously bad for reasons I won't get into at representing those stress concentrations. So I wouldn't really quote that. But given that you did, that makes it look like, if you're doing an analysis of 90-mile-an-hour winds, whatever your design wind should be, if that's what your design wind should be, then you're not showing a lot of factor of safety here, right? So, your factor of safety would be something like 285 or 260, which is like
I don't know, 1.0 something. So it's very small. So if your material, you buy your material and it comes in a little weaker than you expected, or your stock comes in a little bit thinner than you expected, or it's got a ding somewhere and it's, for whatever reason, a little bit, not as structurally robust as you expect. That's kind of what your factor of safety buys you insurance against. And there are a couple of different philosophies on that, and I won't get into it, but I can send you a link to something that NESC put together if I can find that. But ultimately, you don't have a lot of factor of safety here, and in reality, you certainly do, because I don't trust a 260 megapascal result as stress concentration. You certainly have more capability than that. But given that you've put it on here, you're not showing a significant factor of safety, right? And for something that's in the ground and is just supposed to stay there, you're not really, weight or material constrained. You should probably have a factor of safety of something around 2, maybe 3. You're going to have fatigue loading, which could potentially be a concern. And, if you've got fatigue and, at 260 megapascals versus a yield of 285, that's potentially going to fail in a low number of cycles. So, a lot of things that ultimately come down to the FEA isn't really a good representation of what's going on here. I will say, fantastic job showing a soil analysis. I think that's something important to consider when you've got, as you do a post going down into the ground. I appreciate that you looked at that. I'll ask, Dr. Traum said, good job with the hexagon. I'm not sold. And one of the things that I'm not sold on is you said that, the hexagon allows for rotation in the plane without impinging on neighboring panels. I wonder how close these really need to be, and how much in-plane rotation that you're going to do, right? If you're rotating in plane, the sun's still in the same place and the tower's still in the same place. So I don't see that buys you anything. Maybe that's kind of a safety factor, but I wouldn't really expect to get any sort of impingement of one mirror on the next. Is there anything I'm missing there?
Yeah, so our first customer interaction, he actually told us to basically imagine the field as a field of pixels in a TV. And the more pixels you have in a TV, of course, the higher resolution, the better performance. So that's kind of what we are focusing with here, is basically trying to get the smallest area you can to basically pack as many modules as you can in the field. So, Kaylin, can you actually go back to slide 20? So the shape itself won't really affect how it reflects the light. The area will stay the same. So all these have the same area, so they're all going to have the same reflectance. But it comes into the amount of basically buffer area you need so that they don't collide. So
okay.
I know you were saying how close do they need to be packed? Our objective here was to basically choose a shape that allows them to be packed as close as possible to put the most modules on the field and satisfy the customer.
Okay, so I would note that it looks like they're not very closely packed and spaced further out as you get farther away from the tower. So I wonder about that. I would also suggest that your cleaning truck or whatever this little thing is that's going in there probably is going to have to be custom designed to be able to reach, where it's able to reach a hexagon that's sort of on the, I don't even know how to describe it, that's close to it versus one that's diagonal and in. I wouldn't expect that truck is going to navigate around a 3-foot bump in the pattern. So it may have to reach further. So you may be incurring some additional complexity on your cleaning there. And the last thing I'll ask is, you went into a lot of detail about the error in your algorithm versus the requirement of half a degree, and you're well within that. And you've got the control of your motor, which, and I definitely appreciate that you've got the belt drive system that's attaching far out on the mirror, so you've got a much finer ability to control that. But I wonder about the compliance of the structure combined with the error in the motor versus what the tracking requirement is, and if is that tracking requirement like an average over some time, or if it's sort of vibrating in and out of focus is the wrong word, but on and off the target, is that a concern?
So for that, we found that the from that FEA, which I know you're saying isn't a great representation, but we found that the displacement was about a little less than 2 millimeters for the mirror position, which results in a 0.28 error in the mirror position.
I'd wonder about that. I think you're looking at the post and not the mirror itself. I didn't see a lot of structure behind the mirror, so I wonder how compliant that's going to be.
Oh, okay. Yeah.
Okay.
Oh, sorry. I just want to touch on the cleaning operation. The way our field is designed is actually in rows. So the way we imagine is that the cleaning truck would go down the row and basically just spray the modules. So it wouldn't have to like go around it. If you were worried about like irregular vehicle tracking around the mirror for cleaning.
Okay.
All right, we still have about 5 minutes left.
Yeah, I've got a couple of questions. So you talked a little bit about welding the assembly together. Could you go where you discuss that?
Yeah, so for our support structure, we decided to stick with the same material throughout just for simplifying the manufacturing. And since we use sheet metal, it can all be spot welded to hold up together. I mean, it'd probably be the simplest and quickest way to assemble the whole thing.
Okay, I'd just be concerned there. You might not be able to use the same allowables at those points. That those might be your points of concern going forward as this thing ages and is out in the weather for a long period of time. Just something to consider. But I did, like Tom mentioned, I appreciated the soil analysis. I thought that was good. One of the things I appreciated about from your poster, right, was while I understand Tom's things about the hexagon, it was nice how you incorporated that throughout your poster presentation. And then I guess the last thing, if you could go to your cost slide, where you talk about cost. Yeah, so here, when you're going through all that, I still would like to understand a little bit about what were your assumptions going from the prototype cost to the mass production cost. I do think you made a good effort here to drive down your cost towards what the customer is looking for, and you could probably argue, that $100 is very ambitious, right? But just like you to talk a little bit more about how you drove those costs down between prototype to mass production.
So for the prototype mass production, we just assume manufacturing, assembly, and energy would be the same in order to build a single heliostat, just as kind of like a buffer. And then the only thing we could really bring down in cost were our OTS parts and our raw material, in the sense that we would be able to buy in bulk. So that we would get a large quantity for a lot cheaper. And that was the only way that we were able to like save on cost between prototyping and mass producing. I mean, both the mass production price could be the same as the prototype price, but we would have huge amounts of product in order to build it. So that's why our prototype is more expensive, because we went with small quantities for the sense of when prototyping and building, we can kind of figure out what works, what doesn't, what needs to change, what we would need to implement and stuff like that.
You can also think of it as when you're building the prototype, let's say for the fasteners, you buy one pack of the lowest amount of fasteners, let's say theoretically is 20 fasteners. Let's just say our prototype only takes 10 of those. Now you got 10 fasteners in inventory. When you start mass production, those parts that you have inventory goes into that mass production, which brings costs down instead of buying a whole other pack for another heliostat.
I appreciate it. I really think y'all did some good thought thinking out your design here. It's much appreciated.
Then if I could just follow up, I don't mean to be super nitpicky, but you guys have got it looks like 3D printing is one of your fabrication techniques. And you're saying before that your prototype manufacturing costs and your mass production manufacturing costs are the same. Did you consider, instead of 3D printing for mass production, some other plastic fabrication technique like injection molding to drive costs down?
We did not look into that, but that would be a good way to save money, is if we were to get a mold and then have it injection molded. That would probably be the best cost-effective way to do that. But yeah, the 3D printing obviously is the easiest way for a small scale in order to just do one for a prototype.
Yeah, I got you. Yeah, so when you go to thousands of these, there's some crossover point where all of a sudden injection molding, although more expensive up front, becomes cheaper when you've got large volumes. And I'm not sure if you guys have crossed over that point with just a single field of these, a couple thousand of them, but there is some magical crossover point, and that might start to drive down that manufacturing cost as well and get you closer, at least, to the $100 goal. Okay, so so that actually gets us right to 45 minutes. So let's stop there. Hang on. I'm just looking in chat. Okay, so yeah, it's just Tom talking about a little bit about 3D printing. Okay, okay, great. So let's wrap it up there, just for sake of time, because we do have one more presentation today. And let me drop into chat for our panelists that Zoom link. Let's see here. Maybe. Okay, here it comes. All right, so there's the Zoom link to access the final presentation of the day. And we'll thank group number 2 for sharing their design with us. Lots of really good both technical design and also, like I said before, I like the aesthetic design. I think that it's very clever how you guys sort of put it all together and address like different elements, both cost savings and spacing and the aesthetic element. So maybe Tom and I can argue offline about the benefits there, but I thought you guys did a great job. So really appreciate all the work you put in this semester. And we will transition now to the next presentation, which will be the final one for today. So see everybody there in just a couple minutes.
All right. Thank you very much.
Thank you, guys.
Thank you.
Thanks.
Have a great day.
Well done.
Let's go.